Welcome to the Monday Colloquium in the Department of Physics. It's my pleasure to introduce Nadir Jeevanjee, who's here from Princeton. He did his thesis here in Berkeley, and one of the advantages of Berkeley physics is that you can do a lot of different things. And he started off in theoretical physics, working with Robert Littlejohn, and then he decided he wanted to do something different, and he moved to Professor David Rom's Center for Planetary Sciences, where he did his thesis looking at basic models of convection and how it interplays with climate change. And he's kept to that general theme of sort of understanding microphysics correctly and embedding that into bigger simulations and trying to make fundamental predictions based on solid advances in physics. And he's kept to that for about 10 years now. I would say he's done it very successfully. He's been awarded the American Geophysical Society's James Holton Award and the Henry Houghton Award for the American Meteorological Society. This last award in 2025 had the citation for providing robust and comprehensive theoretical frameworks to illuminate complex phenomena in climate physics. Beyond his research, he's also very engaged in outreach. He is the co-founder of Climate Change Conversations, which you can find just by Googling it. And he's an active initiative that brings the where they, a couple of them, go out and give talks and try to talk to people with all sorts of different views on climate change, and try to find common ground and try to agree on things as opposed to dispute them. Or, as I wrote, thoughtfully and constructively engage on climate science. Nadir's talk today is on radiation, convection, and climate. Please join me in welcoming Nadir.
Thanks, everyone. It's a great pleasure and kind of a trip to be here. I got my PhD here 10 years ago and did theoretical physics. Published a textbook on tensors and group theory. And somewhere along that journey, I was, as a theorist, you do a lot of teaching. The grad students here know that. And I was a TA for Physics for Future Presidents, Physics 10, I think. And that was taught by Rich Muller at the time. And that course really opened my eyes to how issues that I was reading about on the front page, renewable energy, nuclear power, the electric grid, and climate change, were underpinned by the fundamental physics that I had learned here. I mean, some of it literally in this room. So I got excited about applying the physics I knew and loved to these front page problems. Around the same time, David Romps, who's here in the audience, showed up here at Berkeley. He himself, a former theoretical physicist, having switched to studying the atmosphere, so we had that in common. And so I jumped ship and began to study the atmosphere, in particular the physics of clouds and convection. And here I pictured some sort of tropical thunderstorms. These are the kinds of simulations that we ran and that I studied during my PhD. After that, I moved on to Princeton for a postdoc. I was in their geoscience department for a couple of years, and I had a fellowship that allowed me some flexibility, and so I actually took a bit of a left turn and started to study the greenhouse effect, radiation, which in some sense is a departure, but as I'll argue today, is sort of the yin to the yang of convection. And what I'm going to argue is that it's hard to understand convection without understanding radiation because they're so interlinked and interwoven. And that's going to be the central sort of message of today's talk. And after that postdoc, there's also a renowned climate modeling center in Princeton, affiliated with the university. And so I crossed the street, so to speak, became a staff scientist there about 6 years ago, and I've been there ever since. And so I'd like to tell you a little bit more about the Geophysical Fluid Dynamics Laboratory. Let's see, can I play this? No, let's go from here. So we build climate models. And the way we simulate climate, it's kind of a brute force approach. We simulate climate by simulating a lot of weather. And so we take the same atmospheric model, solving these same fluid equations of motion on a sphere with rotation. And then you have to add in the physics of radiative transfer, the microphysics of cloud condensation. Oftentimes you have the land surface and you try to model the biology of that. And then you couple all of that to a dynamic ocean, which you can't see here, but you're simulating the full 3D flow of the ocean surface temperatures and interaction with radiation, et cetera. And so as you can see here, I mean, there's a remarkable variety of phenomena just in the atmosphere that you're simulating. You can see the tropical rain band. If you kind of stare here at the equator and kind of take a time average with your eye, you'll see, I'll play that once again because these movies are always fun. So yeah, if you kind of stare along the equator, you can see a band in the time mean of clouds and precipitation. That's your intertropical convergence zone. You see tropical cyclones spinning off. And then you see extratropical cyclones or large-scale, basically mid-latitude weather happening at the higher latitudes. I'm sorry. Full screen. Apologies. Oh boy. Okay. So these models that we develop here and elsewhere, there's probably a couple dozen modeling centers around the globe. And the results from the simulations that we perform, where we kind of simulate historical climate change, we project out to the future. These feed into these government reports, like those that come from the IPCC that folks here are probably familiar with. In fact, GFDL is not just a climate modeling laboratory, but it was the first. So the first numerical simulations of global climate were conducted here by Manabe, who's pictured here some decades ago at GFDL. And you may recall from a few years ago, there's actually a Nobel Prize awarded to a handful or a couple of climate scientists. And Suki was one of them. And I'll have more to say about Suki's contributions as we go on. Something else I want to mention that's kind of related to my own trajectory, and I think it's relevant, especially speaking to a physics department, is about a sort of a culture, a little bit of culture shock that I felt shifting from physics and especially theoretical physics to climate. And so in theoretical physics, you're used to considering objects like the Planck function, something you can derive from first principles on a blackboard. It describes something fundamental and ubiquitous and relevant to many fields of physics. And in the climate science literature, if you look at those IPCC reports, for instance, you won't find any equations in them. You find a lot of charts that look like this. They have the very practical task of trying to summarize what climate scientists know and what we think is going to happen in the future. And sometimes we try to probe what we think is going to happen by taking a lot of different climate models and running them out, some decades into the future and seeing, for instance, how much they warm. But because the climate system is complex and you have to account for the effects of cloud formation and other things that you saw in the simulation, models don't always agree, and you see a lot of these kind of spaghetti plots where you run models, you run them out, they disagree, and then maybe you take a multi-model average and you account for the spread, and that's your result. And so I think it took some effort for me to try to figure out how to be a physicist in that context. And I wrote about this in an op-ed that was published a few years ago by the APS. And so in addition to telling you something about the climate system and about how radiation and convection are coupled, I'm hoping to give you examples of how to bridge a little bit of this culture gap between the physics community and the climate science community by showing how what happens in these models can be understood, often via an analytical or blackboard type understanding. Okay, so I've been talking about this coupling between radiation and convection and how fundamental it is. And that was actually what Manabe got his Nobel Prize for. If you look at the citation, he was cited for exploring the interaction between radiation balance and the vertical transport of air masses, convection. So what is that referring to? So let me give you a cartoon understanding of it, and then we'll get to the brass tacks. So, of course, the climate system is driven by sunlight. That's where all the energy is coming from. Reaches the surface warms up, and emits blackbody radiation in the infrared. But that radiation cannot escape to space because of greenhouse gas molecules, which by definition are just molecules that absorb and emit infrared radiation due to their molecular transitions. And so these molecules, mainly H2O and CO2, absorb most of this upwelling radiation from the surface and re-radiate it back down. So radiation is not a good channel for the surface to get rid of the sunlight energy and come into a steady state with it. So what does the surface do? It does the same thing we do. It sweats. Most of this solar energy that's deposited in the ocean actually comes off the surface in the form of evaporation. And so the surface is evaporating water molecules and also providing sensible heat to the air just above it. And that warm, humid air eventually becomes buoyant and starts to convect. And it rises up, it goes to lower pressure, it expands, and it cools, just like the air coming out of a pressurized bicycle tire. And if it cools enough, the air inside reaches saturation, and you get condensation, and you get cloud and raindrops. And all of that is familiar from the hydrological cycle that you studied in school. But what they probably didn't tell you is that the latent heat that the sun provided to evaporate those molecules off the ocean surface, you get that back when you produce a raindrop. And so in that way, every raindrop is kind of like a little bit of concentrated sunshine. And that solar energy that came in here gets released up here, aloft in the atmosphere, where greenhouse gas molecules can now send it into space. And so what that's telling you is that the cycle of energy, or the flow of energy through the Earth's system, is of course radiative, but also mediated by convection, with water vapor as the key middleman. And so we describe this paradigm as one of radiative convective equilibrium, that the energy flows through the Earth system through both radiative and convective processes. And so Manabe understood this, and one of the earliest models that he built was a model for Earth's climate where he took a global average, averaged over all longitude and latitude, and was just left with the vertical dimension where all these processes are operating. And he'd already built a model of greenhouse gas radiation. He then coupled that to a very simple model of convection, and then was able to simulate the temperature profile of the global mean atmosphere. And he did this for a few different CO2 concentrations, and these temperature profiles matched the global means pretty well. That was encouraging. And in the lower atmosphere, what we call the troposphere, where we have convection and weather, that convection is what's setting the slope here. And of course, the temperature is decreasing as you go up. That's familiar from hiking up a mountain or flying in a plane. And it turns out that the slope can be described with textbook thermal physics. And so these expressions for the vertical temperature gradient, sometimes called the lapse rate, are sometimes homework exercises that you'd have in a thermodynamics class. And this factor over here is the factor you'd get in a dry atmosphere without any condensation. And then this factor over here gives the modulation of that by condensation, and it makes this value a little bit less, a little bit smaller. Up here we have the stratosphere, where there is no convection, and in fact the energy balance is now a balance between UV absorption by ozone and infrared emission to space actually by the CO2 molecule. And so what Manabe found when he increased the CO2 is that CO2 emission increased and caused a cooling in the stratosphere at the same time that you had warming at the surface. And this was an early prediction from these models that has been confirmed in subsequent decades by satellite observations. And there's a boundary between the two, the tropopause, which was simulated interactively by his model, and which will be important in a few slides. And of course, the major sort of implication of this work is that when he doubled CO2, he found some warming near the surface to the tune of about 3 Celsius per doubling, which is still basically our best estimate to this day. All right. And before, this is just a little bit of an aside from RC, but I think it's important to note that after he did these single column calculations, he of course then built global models and made some quite startling predictions that have also come true. And not just about the magnitude of global warming, but about the spatial pattern. And so here's an early simulation where the shading is showing the warming, and there's 3 features that really stick out. That the land warms more than the ocean by about a factor of 1.5. That the Arctic warms more than the rest of the globe by about a factor of 3. And that down here in the Southern Ocean, the ocean around Antarctica, the warming is delayed or muted. And we look at the observations, the vast majority of which came in after this prediction was made. You see those same things: Arctic amplification, land warming more than the ocean and delayed or muted warming over the Southern Ocean. And if you analyze the data carefully, these factors, it's these same factors that show up. So these were real predictions made decades before the data came in. All right. So the question I want to pose in this talk, and that actually I've kind of been asking myself, in the years since my PhD, is what else can RCE teach us? So we already saw some of what Manabe learned with his 1D model, and how some of that was extended by the global climate models that he ran. In addition to that, a tool that we're going to use, and by the way, what I'm painting here is a sort of hierarchy of models. If we're going to learn something in a simple model, we have to then test it in the global models, and vice versa. The global models have so much complexity that to learn something we often have to simplify. And so a third class of model we're going to use is this. I started to run these with my PhD working with David, continue running them at GFDL. And so here, this is a cloud resolving model. You can see the convection being simulated here, but it's just in a patch of tropical atmosphere. And it's doubly periodic, so what comes out one side goes back in the other. But crucially, the atmosphere here, it's sitting over a warm sea surface. I'll play this again. And it's coupled to radiation, just like Manabe's model. So there's radiative cooling happening here in the atmosphere loft. And it's coupled to microphysics. And so you're explicitly simulating the condensation of cloud drops and raindrops, as you can see here. So this will be an important tool going forward. Oh, not sure, sorry. A sec. Yes. Okay. So what else can RCE teach us? So actually, just from this simple picture that I've shown you already, we can draw a conclusion. Because we've said that there's this balance between radiative cooling and heating from condensation. So let's just look at, oops. Not advancing. There we go. So the radiative cooling in the whole column in watts per meter squared we'll call Qrad. And this has to equal the heating from condensation, but that's just the latent heat of vaporization of water, L, times the global mean precipitation rate, P. And so what this is giving us already is a radiative constraint on precipitation. If these guys are equal, then the total amount of precipitation in the, say, annual and global mean is actually determined by radiation. There's this connection between radiation and precipitation. And naively, you might think, oh, well, precipitation is a function of the water vapor in the atmosphere. Maybe that should scale with Clausius-Clapeyron, right, which tells us how much water vapor the atmosphere can hold. And this is, again, something you learned in undergrad thermodynamics, that the water vapor concentration Q in kilograms of water vapor per kilograms of dry air scales with this Clausius-Clapeyron exponential. And so if you look at the fractional change with warming, say with global warming, which we'll call alpha, it's about 6 to 7% per Kelvin. And indeed, that's what climate models show. If you take an ensemble of climate models, have them run the same scenario, you get some spread in the warming that they show. And so you get some spread in the change in moisture, but they all kind of scatter along this line that's in this neighborhood of 7% per Kelvin. What about the global mean precipitation? It doesn't scale at 7% per Kelvin. It scales with a much shallower rate of about 2 to 3% per Kelvin. We're going to call this fractional rate of change eta, and we're going to use that notation throughout the talk. And so something that RCE can teach us is maybe help us to understand, where does this value come from? Precipitation is not increasing with Clausius-Clapeyron. It's increasing at a slower rate, but if precipitation is constrained to balance radiative cooling, then maybe we can kind of turn this on its head and study the radiative cooling to understand how precipitation changes. And this is sort of a familiar thing we do in physics, where if you have some kind of duality or equality, things are complicated on one side, you then study the problem on the other side. So that's what we're doing here. All right, well, if we're going to turn this precipitation problem into a radiation problem, then we have to learn some radiation. And so here's the absorption spectrum of water vapor. The mass absorption coefficient as a function of wave number. This is just proportional to frequency, inversely proportional to wavelength. 1,000 inverse centimeters is about 10 micron. And the reason I'm focusing on water vapor is because, as you can see here, it's got both a rotational band of absorption and a rotational vibrational band, which covers just about all of the thermal infrared. That's not true of the other greenhouse gas molecules. CO2, for instance, would just be in a narrow band around 600 inverse centimeters. Water vapor, because of its rotational modes, because it's a polar molecule, can absorb over a broader range of wavelengths. And that's why, in this sense, it's the most important greenhouse gas. All right. Here's the optical depth as a function of pressure and wave number. And the optical depth, just to remind you, is just the product of your absorption coefficient times the mass of absorber above you. And if you think about that for a second, it's just really the total effective area, cross-sectional area of absorbers above you, divided by your actual area. And this contour here is the tau equals 1 line, which I'll talk about in a moment. And then here is the radiative emission to space as a function of pressure and wave number. So this is where those photons that escape to space are generated, again, as a function of pressure and wave number. And this is a flux divergence, which can be written this way in terms of the Planck function. The gradient of optical depth, which is like the emissivity of your layer. And then this exponential, which is just how much of that radiation makes it out to space. And the reason that, and you can see that this curve is kind of following this tau equals 1 curve. And so radiation tends to maximize from tau equals 1 because it's a sweet spot. If you have absorbers whose density increases exponentially downwards, which is true for water vapor and for CO2, in z coordinates, just because density increases downwards, and for water vapor there's also this Clausius-Clapeyron scaling, then if tau is less than 1, you just don't have enough emitters. If tau is much greater than 1, then your view of space is blocked. That's this exponential over here. So tau equals 1 is the sweet spot. All right, so that's the basics of radiative transfer in one slide, but I haven't taken advantage of the special thing about water vapor, which is its Clausius-Clapeyron scaling. Its concentration scales with temperature. And if I put this expression for Q in that integral that I just showed you, and I kind of do the integral and massage it, I get something that, again, you integrate an exponential, you get an exponential. So I get something that, again, is just dominated by this exponential dependence on temperature. But this actually has a really important consequence. This is saying that if I go into the atmosphere and I want to know the optical depth of water vapor, I only have to know the temperature at that point. I don't have to know the pressure. I don't have to know the height. I don't care how far off the ground I am. And I actually don't care what the temperature at the surface is. I just care about the temperature here. And knowing that and the lapse rate, which is constrained, tells me about all the water vapor above me. And so that actually has really important consequences, which were appreciated almost 100 years ago by George Simpson. This is a paper he published in 1928. And here's a manifestation of that. If I take, say, single column calculations like Manabe's, and I run it at 4 different surface temperatures, and then I plot here the emission temperature, with temperature increasing downwards, just like it does in the atmosphere, as a function of wave number, you see that as I increase the surface temperature, in the window region, where the absorption is small, my emission temperature increases. But up here, where water vapor is absorbing, I barely get any increase in the emission temperature. When I'm looking down at space, from space at the Earth and these wavelengths, I'm just seeing the tau equals 1 temperature determined by this equation, and I don't really know what the surface temperature is. All right, so this is going to have consequences for the radiative cooling and the flux divergence of the atmosphere. And I just convinced you that temperature is the thing that water vapor emission cares about. It doesn't care about height, doesn't care about pressure. One of the things you learn in your upper division physics classes is to use the right coordinate. And so what this previous slide suggests is that in the vertical, especially in the troposphere where I have this monotonic decrease in temperature, maybe I should use temperature as my vertical coordinate. And so I write my flux divergence in temperature coordinates. And so I've got the derivative of tau with respect to temperature, and then I've got my Planck function. So everything here, again, still just depends on local temperature. It doesn't care about the height, the pressure, or what's going on down at the surface. If I integrate that over the spectrum, that doesn't change. And so what's telling you is that this flux divergence should be independent of the surface temperature. So let's check that. So we take some cloud resolving simulations at a handful of different surface temperatures. I use temperature as a vertical coordinate on the y-axis, and I've got my flux divergence on the x-axis. And I do it for a relatively cold surface temperature of 280 Kelvin. And I get this profile. But what this is telling me is that if I raise the surface temperature, the flux divergence profile I get at the higher surface temperature should be the same up here and should just extend a little bit further downward. And that's just what you see. And if I raise the temperature a little bit more, same thing. I get the same profile, just extends a little bit further down. And if I continue on in temperature, I get the same thing. And this only holds when I use temperature as a vertical coordinate. If I do this in height or in pressure coordinates, I get spaghetti. Furthermore, if you look at where the temperature goes to zero, where the flux divergence goes to zero, that's where the rate of cooling goes to zero. And convection no longer is balancing rate of cooling. That's the tropopause. That's where the convection stops and the stratosphere takes over. And just from this figure, you can see that it looks like the temperature of the tropopause seems to be fixed. And so that'll be another important ingredient going forward. And finally, the thing that we were interested in was in the column rate of cooling, because that's equal to the precipitation. The precipitation is the thing we care about. And the column rate of cooling is just the area under this curve, right? It's just the integral of the divergence is the flux difference between the top and bottom. So here's QRAD. Here's the thing we want to learn about. And the reason that we went through this whole business about going into temperature coordinates and learning about H2O radiative transfer is if we want to know how this thing changes with surface temperature, well, we've learned some things. We've learned that this profile actually is independent of surface temperature. And furthermore, it looks like the tropopause temperature is independent of the surface. And in fact, you can think of this tropopause temperature as just being the tau equals 1 level of your most absorbent wave numbers over here. And in fact, there was a graduate student. Uh-oh, come on. Oh, I think I'm out of battery here. No, maybe not. There's a graduate student, Brett McKim, who took up this question. And he also ran some single column calculations, varying the surface temperature and then studying how the tropopause temperature evolved. And it's pretty insensitive to the surface temperature. And in fact, you can write down an equation that just says that the tropopause temperature should be this tau equals 1 level. And that equation agrees very well with the simulations. And so going to this equation, you can now differentiate it with respect to surface temperature. But the integrand is independent of surface temperature. This lower limit is independent. And so you just apply the fundamental theorem of calculus, and you get this very simple expression. And it's just saying that the change in this radiation, and hence the precipitation with warming, is just given by the flux divergence at the bottom of the atmosphere. And so there's a very simple picture that goes along with this. Here's my flux divergence as a function of temperature. When I do some global warming, this profile doesn't change. I just add more cooling at the bottom. And the magnitude of this cooling is just the value of dTF at the surface. And so the picture here is that the rate of cooling increases because the troposphere is deepening from below in temperature coordinates. That's what's happening. And you can test this expression. Here's the rate of cooling and the precipitation as a function of surface temperature. Precipitation's in the blue stars, rate of cooling's in the black. They start to diverge a little bit when you're colder, but at temperatures around Earth's average temperature, it's a pretty good match. And the red line gives the slope of this curve as predicted by this. And you can see that the red lines are a good match to the overall curve. Furthermore, this gives us insight into this number of this 2 to 3% per Kelvin. Because if the area under this curve, it has this roughly triangular shape, then the area is quadratic in the difference between the tropopause and surface temperature. And so the logarithmic derivative is then just this factor of 2 over this difference in temperature between the surface and the tropopause. But this difference is about 100 Kelvin. And so 2 over 100 is about 2% per Kelvin. So this 2 to 3% per Kelvin number is really set by the depth of the troposphere in temperature coordinates. And so using this physics that we've learned about radiative transfer, switching coordinates to temperature has sort of explained this number that previously was just a model result. All right, so we have this radiative constraint on precipitation. that precipitation has to follow the total radiative cooling. Models told us it was 2 to 3% per Kelvin, but by thinking a little bit harder about this, we're able to understand that, write down an analytic formula for it, and get some insight as to where this number comes from. So that's the first part. So now going back to this plot from Held and Soden, we have the moisture scaling at 6 to 7% per Kelvin. The precipitation scaling, which is different at 2 to 3% per Kelvin, there's a mismatch there. And so it's not the case that you have the same frequency of convective events, and they just get moister, right? There's this mismatch between how much each event moistens, or how much the moisture in the atmosphere changes, and the total amount of precipitation has to have consequences. And so what are some of those consequences? So that's going to be the next question. And to do that, this radiative constraint on precipitation that we had before was an integral constraint. It was a constraint on the total amount of radiation, infrared radiation leaving the atmosphere, and the total amount of precipitation. But in physics, we also like to have differential versions of our constraints. So what's the differential version of this RCE constraint? So on the radiative cooling side, we can just take a flux divergence. We use z coordinates for the moment. We'll get back to temperature. And then on the convection side, we can look at the condensation heating, the differential condensation heating in the layer, which is just the latent heat L times the condensation rate, the kilograms per meter cubed per second of water vapor condensing. And if I take that, I can massage it a little bit. And I can write this condensation rate in terms of the mass flux m, the total amount of moist air rising up in kilograms per meter squared per second. So you can think about that as just the total amount of convective air rising. This is as seen, say, from satellites or seen in the observations, in the simulations. And in the simulations, we go in and we look at the grid cells that are cloudy and moving upwards, and those give us the convective mass flux. And so the condensation rate is this mass flux times the gradient of moisture inside the cloud, right? The cloud, the water vapor, the saturation value decreases as you go up because it's getting colder. And so as you go up, the amount of vapor that's allowed to be in the cloud is decreasing, and so moisture gets squeezed out. And there's this moisture gradient describes that. And this moisture gradient is precisely what's responsible for the difference between the dry temperature gradient and the moist one. And so it turns out, the way the math works out, is that the moisture gradient can just be written as the difference in these temperature gradients, where I'll just remind you that the dry value is this one, and the full value is this whole expression. And so now we've got radiation on this side, thermodynamics here. We can solve for the mass flux. And then we can also convert to temperature coordinates, because we found before that this didn't care about what was happening at the surface. And this is governed purely by thermodynamics. And so what this is telling you is that the amount of convection that you have, the spatio-temporal frequency of it, is determined by this competition or balance between radiation and moist thermodynamics. So we're going to try and leverage that. All right, so we saw already that this is independent of surface temperature. And this is a function of how much moisture is in the air, which increases with surface temperature. And so that's telling you that the mass flux should go down, but again, only if you're in temperature coordinates. And so we can look at that in our simulations. So here's the profiles of mass flux for 4 different surface temperatures. Here's the coolest one. Again, temperature on the vertical axis, mass flux in kilograms per meter squared per second of cloudy, moist air rising up. And you see that indeed, the mass flux decreases really, pretty cleanly at all temperatures with warming as you warm the surface, just the way this equation predicts. And this doesn't work if you choose a different coordinate system like pressure. Again, you get a little bit of spaghetti up there. What about GCMs? This was all done in these kind of idealized cloud resolving models simulating a patch of tropical atmosphere. Does this hold up in a global simulation with all that additional complexity? And so here we spun up GFDL's latest and greatest climate model. In these climate models, the resolution is coarse. You have to parameterize the convection, but that's part of the model. And so what I'm showing you here is the parameterized mass flux across the tropics. And you see this sort of tropical band of convection that you also saw in the animation. You see mass flux lighting up over the rainforests as well, which is what you'd expect. And so I can take this whole complex picture and I can just take an average over the tropics and look at those profiles. And I can do that in a simulation of global warming where the surface temperature is gradually increasing. And this is what I get. Here's, again, mass flux as a function of temperature as a vertical coordinate. And you see the mass flux, again, at each isotherm gradually getting weaker as the simulation goes on and the warming gets larger. And so that's a nice confirmation of what we saw in the simplified model, that this physics seems to carry over to the more comprehensive setting. Okay, so if we think we have a theory, then it should not only tell us the sign, but it should tell us something quantitative about this decrease. And so this is where I work with the postdoc, Andrew Williams at GFDL. And he looked at this across models to get a sense of how robust this is. So first he started with an ensemble of cloud resolving models. So simulations like this, but coming from different centers and making different assumptions about the microphysics and the radiation. And here again is, and he had the smart idea to look at the relative decrease in convective mass flux in percent per Kelvin, again as a function of temperature. And you see that the gray are profiles from individual models. The black is the multi-model mean. And you see that it's actually quite tightly constrained. And that pretty much all the models give you a fractional change in the mass flux throughout the troposphere of about 3 to 4% per Kelvin. And then we also looked at this in GCMs. And again found something quite similar, that the profile is relatively uniform and you get a decrease in the mass flux of about, again, 3 to 4% per Kelvin. Oh boy, this really's got a mind of its own. All right, I'll keep doing this from back here. And this 3 to 4%, this robust 3 to 4% per Kelvin decrease can be obtained just by analyzing the thermodynamics of this denominator using the formulas that I showed you. All right. So we have this mismatch between how moisture and radiation scale with global warming. And by leveraging what we already learned about radiation and this flux divergence and temperature coordinates, we got this expression for the mass flux and found that you get a pretty robust decrease in the mass flux of about 4% per Kelvin. So what does this mean? I mean, this convective mass flux is a little bit abstract. It's the amount of convection that you have in the atmosphere. But if the amount of convection decreases, this should manifest in the spatiotemporal frequency of convection, right? If we have less convection, then we should have less rainfall events, fewer thunderstorms. And so this should, but at the same time, we know that the moisture is increasing, and so maybe the thunderstorms that we do have will be more intense, and the rainfall rates will be higher. So what are the implications of all this for precipitation? This is one of the impacts that people care the most about. So again, we expect the mass flux to decrease with 4% per Kelvin, and that this might manifest in the frequency of convection. We know that the moisture is going to increase at about 7% per Kelvin. That might give us an increase in the intensity of the rainfall. And these ideas are out there. And so there's papers looking at both in the observational record and at models of how heavy precipitation changes. And a lot of work on droughts and how precipitation is becoming less frequent in many places across the globe. Kevin Trenmouth in a paper kind of even came up with this cartoon to describe this. It never rains, but it pours. And so while this kind of idea is out there, this gestalt is out there, it's been hard to pin this down. So some studies have looked to see, does extreme rainfall scale with Clausius-Clapeyron? And the answer is, it depends, sometimes. Some studies find it, some studies don't. And a question that's missing is, how do these things combine to tell you about how the whole distribution of precipitation is going to fall? Not just the extremes, but the whole distribution. So that was something we wanted to look at. And so we did that with the current graduate student, Carlos Ordaz, at the City College of New York, who I'm collaborating with. And so for starters, you can actually just take a look at these same simulations, cloud resolving simulations that we've been looking at. And you can just take a snapshot of the surface rain rate. And that's what I've done here for these 4 different simulations. And the color bar, you'll notice, is actually doubling in its upper limit with every 10 Kelvin. That's Clausius-Clapeyron scaling. 7% per Kelvin by the rule of 70 is a doubling for every 10 Kelvin. So the color bars are CC scaled, and just by eye, you can see that the rainfall rates are kind of keeping pace with this Clausius-Clapeyron scaled color bar, and the convection events look like they're becoming less frequent. But can we make this eyeball impression precise? That's the question. And so the quantity we're going to focus on is the amount distribution. And this is, and so basically all the convective events that we're seeing here, you just aggregate them just grid cell by grid cell into a distribution over the course of the simulation for each different simulation. And so if you integrate this amount distribution with respect to R, then you just get the total precip. And this is just equal to the rain rate times the PDF, the frequency distribution. Here's what these amount distributions look like for 2 of the simulations. They peak at a characteristic value, but that characteristic value kind of shifts with warming. And the area under the curve is, of course, just the total precip, which also is increasing with warming at 2 to 3% per Kelvin, as we've been discussing. And it turns out that this shift looks like it follows CC scaling. And then you can see this in this plot where the peak moves over by about a factor of 2 for a 10 Kelvin change in surface temperature. And so we make an ansatz that this amount distribution should just shift over by CC scaling. So I've put this alpha, the CC scaling factor, in the, because it's the log change in moisture. So I put in the exponential times the change in surface temperature. So this is just a shift of the amount distribution by CC scaling. But then you want to get also this, but the shift by itself won't change the total rain amount. So you have to scale it by this eta factor, which was the logarithmic change in the precipitation. So it's just the simplest thing you can think of to do. Just shift the distribution over by Clausius-Clapeyron and then scale it up to get the total amount of rainfall that you know that you have to have. And even though it's the simplest thing you can think of, it hadn't been done before. But in the simplified context, it seems to work. So here are the amount distributions for those 4 different cases. The actual amount distribution is in black, and the prediction that you get by, say, taking this one and just shifting and scaling it over here is what you get in orange. And you see it's really an excellent fit for these 2 simulations, a little bit of a degradation here. We also looked at this across different cloud resolving models and found that it compared favorably. All right, so what are the implications of this shift and scaling? Well, so here's what the new amount distribution looks like. But the amount distribution is related to the frequency distribution. And if you just work out the consequences for the frequency distribution, you find that you do also get a shift by CC scaling, but then what you get out front is actually a decrease. Because if I took all the convective events that I had in my base climate, I just kept their frequency the same, but just shifted them to higher rain rates, I'd get 7% more rain per Kelvin. But I know that I should only get 2 to 3% per Kelvin more rain. So I have to decrease the frequency of events to get the total amount of rain right, and that decrease is just a function of n minus alpha, the fractional change in P and the fractional change in moisture, which again, this is about 2 to 3% per Kelvin, this is 6 to 7% per Kelvin, and so I get a minus 4% per Kelvin change in the frequency of rainfall events. And so that, of course, is the same number that we got when looking at the change in mass flux. So we're getting a consistent picture here, and that's what this figure is emphasizing, that as I warm, these different metrics of the frequency of convection, whether I'm measuring, and basically this is just, everything's normalized to the values at 280, and so you're just seeing the fractional changes here on a log scale. So a consistent fractional change would be a straight line. And you see that whether I measure the mass flux or the convective area, I didn't talk about this much, but if you just take the convective events that I've identified and project them down to the surface, that defines a convective area, and you can look at how that changes. And you can also look at this alpha minus n, and these all are decreasing. by about 4% per Kelvin. And so you're getting this mismatch between how radiation scales and moisture scales is giving you a consistent picture with implications for the distribution of rainfall. And so indeed, you expect events to get less frequent, but more intense. And that's what we've got here. And that's what I have for you guys today. And just to kind of zoom out a little bit, I think of these as good examples of the physics of climate, where we're asking big picture questions about how does the global amount of precipitation change? How does the spatiotemporal frequency of convection change? What are the implications of this for precipitation? Questions that we ask in climate science and that are central to the field, but trying to do it in a way where we can write something down on a chalkboard, reason from physical principles, and that's embodied in these equations here. And this, this sort of 10-year odyssey through radiative convective equilibrium and working on these topics has kind of been an attempt to, sort of bridge this culture gap that I was talking about in the beginning, and that I discussed in this piece. And the other point I should make here is that this hierarchy of models is critical to doing that. And I hope that's been evident throughout this talk. And maybe as a last note here, this idea of the coupling between radiative convection is such an enduring idea. And in physics, we have lots of ideas that just continue to be touchstones for the field, whether it's how space and time are coupled together, how space-time coupled to energy and momentum, or how symmetries and conservation laws are intimately tied to each other. For climate science, this is kind of a paradigm that's maybe analogous. It started with Manabe and his early work there, and just those results themselves, were enough to kind of put climate science on the maps in terms of physics. Thankfully, Manabe's still around. I saw him just a few months ago, and it's been a privilege to kind of carry on this line of inquiry and carry on his legacy. So with that, I'll thank you, and I'm happy to take questions.
Thank you very much for the great talk. We have time for some questions.
Yes. So when Manabe predicted the spatial pattern of global warming, was it mostly just the coupling between radiation and condensation, or were there a lot of other variables he took into account?
Yeah, that's a great question, because I kind of introduced that as a little bit of an aside. So obviously the stratospheric cooling was something that he just saw in the one-dimensional model, and that was purely radiative. You don't even need convection for that, right? If you increase the CO2 up there in the stratosphere, it emits more radiation to space, upsets the balance with ozone heating, and you get some cooling. It's a great question about the physics of these different parts of the spatial pattern. The land ocean contrast is understood more or less in terms of moist thermodynamics. So I think that is something that you can get. You need a little bit of tropical dynamics to figure out how the ocean talks to the land in the horizontal. So it's not just radiation and convection, but a lot of that you can do with the physics we talked about here. Arctic amplification is a more complicated story. You do need the ice albedo feedback, right? When you melt ice, you're replacing a bright surface with a darker ocean surface. And then also the fact that when the moisture increases, it increases more near the tropics than it does at the poles, so you're able to transport more of that heat poleward. So yeah, a lot of this has physics that goes beyond RCE, but I didn't touch on it today.
Other questions? I'll ask a question. Oh, yes.
There's one right there.
Oh, okay. Great talk. Thank you so much. I learned a lot. I'm curious if you've looked now, we have a record of warming and a record of data, and have you validated some of these predictions with active data?
Yeah, great question. And so, so this is the one sort of observational plot, that I showed, not for the theories that I talked about. So temperature is one of the most, is the quantity that we've probably, observed most robustly, and it's also much more continuous than a variable like precipitation. And so our precipitation measurements, we don't have the spatial coverage, we don't have the records going as far back, and it's a much noisier variable. And so people have looked to see whether you can discern this increase in global mean precip with the short, basically satellite record that we have. And there's nothing conclusive as of yet, especially if you're trying to be quantitative about that. In terms of rainfall, like I said, there are some studies that if you aggregate rainfall data over spatial areas that are large enough, say all of the US over all of Europe, you can see some of this. So for instance, you do see a Clausius-Clapeyron scaling in the intensity of extremes. And one of the things we want to follow up on, the work that I was showing about rainfall is happening right now. And so one of the next things to do will be to take the full distribution and see if we can see this shift in scaling. Yep. Hey, Jeff.
Ask a slightly abstract question.
Yeah.
Everything you've talked about is moisture driven, both from the radiation and the convection.
Yeah.
So you can imagine a planet like Earth,
Yep.
which was perhaps a lot colder,
Yes.
and the radiation starts to become dominated by CO2 and the convection becomes more dry. Does it gradually change your picture, or is it suddenly change to a dry picture, or how do you make that transition?
I think it's probably continuous. You saw hints of this in this figure that I didn't linger on for too long. But so if you look here, you can see that the precipitation doesn't quite match the radiative cooling. And that's because the sensible heating, the direct just transfer of heat from the atmosphere, from the surface to the atmosphere, is playing a bigger and bigger role as you get colder and Clausius-Clapeyron gets smaller and smaller. And so it's just harder to have large amounts of evaporation. So yes, you would gradually transition into a regime where condensation heating from moisture is less and less a dominant part of the energy budget. I think actually though that if you go back to radiation, so yes, I think thermodynamically the role of moisture gets less important gradually. As far as radiation though, water vapor is able to, maybe I'll do this one. Water vapor is able to emit to space even from very cold temperatures. And so even though the concentrations of water vapor up here are very small, the absorption coefficients are sufficiently large that it would still be the dominant greenhouse gas, even in say a snowball Earth or something like that.
What would be the optimal set of instruments for you to collect enough data to validate these precipitation models?
For global mean precipitation, we may be getting close. I haven't checked in on that. There were some papers in the late 2000s that looked at this and came to different conclusions, and I don't think people have really kind of gone back to it since. I actually don't know why, so that's a good question. That's for the global mean. In terms of the distributions, I haven't given a lot of thought. I don't know, I would guess that, certainly over the US, I think we've got, over the US and Europe, I think we do have pretty good observing networks. And like I was saying, we may be able to test some of these ideas even now. Globally, I think the rest of the globe is pretty far behind in terms of the density. And so, that's something that's a huge concern right now, especially with, what's happening politically and funding for science broadly, which everyone here is thinking about, but certainly for climate observing. The satellite systems that we use for global observing are threatened, and even the in situ measurements, especially say in the ocean, where we just recently, in the last 10 to 15 years, were able to put together this Argo network that has quasi-global coverage of sea surface temperature, salinity, et cetera. It's not a long record, and we really need it to be extended. Not sure what the future is going to be of that.
This is not exactly a physics question, but I feel like I'm in a doctor's office watching the blood pressure go down of a dying patient. Not to put too fine a point on it, but have you run into any studies from political science or economics about the various proposals for trying to stop this, hemorrhage of our coolness. Have you seen anyone doing studies about the relative effectiveness of trying to change this problem?
I mean, there's vast literatures in whole academic departments, working on different aspects of it, whether you're talking about policy or technology. And of course, something people are talking about now is geoengineering, deliberately intervening in the climate system itself to, say, reflect more sunlight. So yeah, there's a lot going on, and that's a subject for, a whole series of lectures. But yes, a lot of thought going into it.
Okay. Can I follow up on your geoengineering comment?
Sure.
So one of the questions people ask about geoengineering a lot is if you do it in a radiation balance way, what does that do to the rainfall patterns?
Yes.
So are you in a position to answer that for us in a simple way now?
No. Yeah, so that is a very hot topic of research, right? If you try to, say, offset the global warming we've had by, say, putting up reflective particles in the stratosphere where they're longer lived than in the troposphere, what does that do to rainfall patterns? So one thing, I focus on the things that we could try to constrain from, say, thermodynamics and radiation. Of course, there's a lot of complexity that we can't, and certainly papers like this, there's, regional variations that go beyond the radiation and thermodynamics that I'm talking about here. And so even geoengineering aside, there's lots about how the circulation will change under global warming, just regular garden variety global warming, that's not well constrained by models or by theory. And definitely, in the subtropics, over the arid zones, there's a lot of uncertainty, disagreement amongst models. Vulnerable regions like the Sahel, for instance. And so then you add geoengineering to the mix, where now you put some particles in the stratosphere. Those particles are going to reflect sunlight, but also absorb sunlight. They'll change the radiation budget of the stratosphere. They'll change the temperature. Those temperature gradients in the stratosphere, there is a circulation in the stratosphere that then affects regional temperature patterns, down here in the troposphere. And so that's a big unknown. So there's people working right now to say, okay, under different geoengineering schemes, what do we think the impacts would be on circulation patterns? I'm not sure if they'll find things that are robust, because again, these things were already model dependent just under CO2-driven global warming. So that's going to be a tough problem. But there's a lot of attention directed to it right now, as far as I can tell.
One last question.
This was a great perspective on changes in Q, changes in P, and then the difference between the 2 and 3% versus 7% and how frequency plays in there. Is there an easy way to extend this to changes in V times Q, so just polar heat transport, which might increase with Clausius background, but apply some of this frequency perspective to how polar heat transport might change in terms of the frequency of these?
Right. So I sort of think of that as actually an additional ingredient that you might combine with this. So what Ankur was referring to is that when he said V, you were talking about the meridional. Yeah. So we have large-scale circulations, which I haven't talked about, but you have the Hadley cell, the Walker cell, these large-scale flows. And there's a paradigm for the geographical pattern of precipitation change called the wet-get-wetter paradigm, that places where the atmospheric circulation converges moisture, they'll converge more moisture because moisture scales with Clausius-Clapeyron. And places where moisture is diverged, like in the subtropics over the subtropical oceans or subtropical deserts, that even more moisture will be diverged and they get less precipitation. So something I'm wondering about for future work is, can you combine these things? Because the global mean change in precip doesn't tell you about how the regional mean precip will change. But if the wet get wetter will, then you could combine that with Clausius-Clapeyron and with these distributions to then maybe find out how these distributions will change at the regional level. So I think that would be an additional ingredient we want to bring in.
Then let's say Nadir again.
All right, thanks everybody.
And he's here for a couple minutes if people want to come down and question.
All right.